Welcome back, everyone, to the day three of CUDA programming series. And as promised yesterday, we'll be learning about shared memory as well as how to optimize the naive matrix multiplication that we did yesterday. So, uh, just to revise how the naive implementation worked is the kernel was something like this. We calculate the row and column using the block dimension and thread index formula. Let me write it down if you forgot. So row was calculated as block dimension dot y times block id dot y plus thread id dot y. And if we replace the y with x, we will get the column part of it, right? And then we iterate along the k dimension and aggregate the products between a and b. So just to revise how matrix multiplication works is we do calculate a particular row and column element of C, which is the output matrix using A and B, and it goes from 0 to n in the inner dimension, where n is the size of the matrix. And then we multiply r comma k of A and k comma C of B. So all the elements in a row of A and all the elements in the column of B will be multiplied and summed together, and finally the result will be stored in r comma c element of C, right? And that is basically how it is supposed to work. Now we need to understand what happens when we invoke a particular, or what happens when we define threads per grid or blocks per grid, right? So threads per block, apologies for that. So suppose you are saying that there would be, in matrix multiplication, we will be invoking a two-dimensional grid of blocks as well as 2D block of threads. So how it looks like is, suppose you are invoking four blocks, 4 by 4 blocks per grid, as well as let's not make it 4 by 4, just to visualize. Let's do it 2 by 2 blocks per grid as well as 2 by 2 threads per block. So how it will look like is, um, let me take a shape. Okay, no shape is there. Strange. I don't know how to draw a shape here. Oh, here it is. This is a grid. So all of them are same dimension. So apologies for not drawing that. Now this is a block. Let's say 0, 0. This is a block 0, 1. This is a block 1, 0. This is the block 1, 1. Now what is 0, 0 and 0, 1 are? Suppose we are taking just one block of it. So this is a grid, and within these grids, there are four blocks. So as mentioned, we are defining 2 by 2 blocks per grid. Now block 0, 1 means block ID X would be equals to, let's say, what? Maybe it is 1, block ID Y is 0, right? You can define it like this. Same goes for B1, 0. The X dimension, let's say, is 0 and Y dimension is 1, identifying the row and column. Now within each of these blocks, so let's take a block for example. So this is block 0, 1, which is second block in the grid. It will also have threads. And since we defined 2 by 2 thread hierarchy in a particular block, so the thread can be written as T00, T01, T10, T11. Now, when we are trying to do a naive matrix multiplication, we need to calculate the row first and the column next. Then the formula of row is block idx dot y. So y in this case, let's say, is it is what it is 0. Block dimension dot y is 2. Thread idx, same goes for here, is 0. So it will handle 0. Um, Again, C is block dimension dot x, which is block ID dot x, which is 1 times 2 plus thread ID is 0. So it will handle 2. So which element it will handle is C02 in the original matrix. So C will have n by n elements, and out of those, this particular thread 00 of the block 01, this particular block will handle the C02 element, right? Same goes for if we calculate, let's say for T11, R will be equals to 0 times 2 plus 1 equals to 1. C equals to 1 times 2 plus 1 equals to 3. So it will handle C1 comma third element of it. I hope I'm correct with this calculation. Right. And you can also uh, try to do it on your own for all the elements and understand which thread will calculate which R comma C element of a particular output matrix C. Now, in the code, if you remember, I'm telling it again, we calculate R, C, then iterate over K from 0 to N. And where is this K 0 to N is coming? It is the inner dimension, right? This one is the inner dimension and we iterate over it, aggregate the sum. And in this, we do a DA is, let's say, the device array A, and we do I comma K, or the B1, which is K comma J, multiply them together and store the results, right? Now you will observe that these particular elements, both from A and B, are accessed very frequently from the global memory. Now, each thread in a block, you need to understand this very carefully. Each thread in a block has access to global memory. So if you're invoking n by n number of threads, all of these n square threads will have access to the global memory. The benefit of global memory is it is huge. You can store a lot of elements in it, but read write access is pretty slow. So any operation that includes reading and writing from it is pretty slow. And in the naive kernel, we are very frequently reading from the global memory for DA and DB, right? All elements of a row of A and all elements of the column of B are being read very frequently. And this very frequent read process is very slow. So you will also observe, if you remember the results correctly, we saw around 450 G-flops per second in the naive kernel and around 9,000, was it 9,000? Sorry, it was 4,000 G-flops per second in the CuBLAS implementation. So our CuBLAS implementation was around 10 times faster than the naive one. So the goal is to close this gap. We cannot promise to highly optimize like the assembly instructions that they have written and try to match the performance of CuBLAS, but we can try to close this gap as well. Now, apart from global memory, there is something called shared memory, right? And each block has its own shared memory, which inherently means all of the thread. So let's say there are n square threads in a, not n square, let's say some x square threads in a particular block. So all of these x square threads can access from the shared memory. Now you will ask, why do we need a shared memory over global memory? So although the shared memory has a very low memory bandwidth, it can store small number of elements compared to the global one, but the read time to read from it is extremely fast. It is somewhere around 10 to 100 times, depend on your structure of the kernel and the GPU as well. But generally, I have seen 100 times faster read access written in a lot of places. I have not verified it personally, but this is something that is interesting. That the read from the read speed, or the time taken to read from the shared memory for a particular thread or all the threads in a block, is much faster than what we have uh, from the global memory. Now, the major challenge in the naive kernel is each time we are running in the we are running from 0 to n in the inner dimension for both a and b, and we are doing it again and again. We are reading all the n elements, both from a and both from b, multiplying them, and all of these operations are taking from the global memory, which is pretty slow. So we need to do something about it, right? And there comes the concept of using shared memory with tiling. So tiling is a very self-explanatory word. So instead of calculating entire C at once, we will divide C into small tiles, each of size, let's say TS. So TS is our tile size. It can be 16 or 32 or 24 or 64, maybe anything. So, and we need to keep this tile size same as our block size. It is very easy to understand what is going on. And how it works is each tile will loop over A, will loop over B. Each of the thread will store some elements in the shared memory. And then when we are going in the inner dimension, again from 1 to n, or 1 to n, then we can directly read the elements required from the shared memory itself, and we do not need to go to the global memory again. So this is the only benefit of it, but it is a huge one, that when we are fetching elements of, let's say, I comma k and k comma j, all these two all these elements, instead of reading from the global memory, can be fetched directly from the shared memory as well, right? So just to revise it again, there will be a thread, and each block will have multiple threads like this. All of those threads will have access to a shared memory. So we will bypass global memory, do not read anything from it. Instead, we will read whatever is required from the shared memory itself using an approach called tiling. And we will also look at the code, and we will understand line by line of how it is working. Let's look at the code right now. I'll just focus on the kernel as it is the most important part of it. Let me zoom in a bit. Yeah. Now we are defining, we are defining the tile size. So you can experiment around with tile size. I'll also show you how varying the tile size affects the gigaflops per second metrics of the particular kernel, and how it slows it down or speeds it up, right? So we have defined the parameters. They are DA, DB, DC, and N. N will be the matrix size, and DA, DB, DC are the uh, matrices that are stored on device, which in our case is, if you remember, it's GPU. Host is the CPU. Now, as usual, we are again calculating the row and column. So moving back, what these row and column do, they tell which thread will work on which element of C. So there will be multiple number of threads, and we need to identify a particular thread will be working on what element of C. In this case, let's say R and C, and R and C will be calculated, row and column will be calculated using this formula: block dimension dot y times block id dot y plus thread id dot y. Same goes for column as well. But they also tell us one more thing. They also tell which row of A and which row of B to work on. Suppose row value comes in as 0, column comes in as 2. So we will calculate the value of C0, comma 2 using the first row and the third column, or the 0th row or the second column of B, right? They also tell this one important thing. So you need to remember that part. So I hope this is clear. Now, a shared memory of a block can be described using the keyword called shared. So what we are doing is we are creating two arrays, each of size tile by tile. So consider it like this. There will be two arrays AS and BS, both are shared memory, and there will be the size tile or TS, whatever you want to say. Total number of elements it can store is TS square. So let's say we have defined 16. So each tile will have 256 elements. So we can read very fast all of these 256 elements from the shared memory, not global memory. So you will see it is smaller in size compared to global memory because let's say if n is 100, then in global memory we are storing 10 to the power 6 elements compared to just 256 in the shared memory. But this is where the speed is coming from. You're storing less, but since shared memory is closer to the processing unit on GPU compared to global memory. So let's say global memory is here, shared memory is much closer to GPU, and the access is much faster. It is similar to L1 cache and L2 cache and registers and everything. So the closer you are to your processing unit, the faster your speed of accessing is going to be. That is the general concept. Then we are just saving the thread ID of in the direction and the y direction in tx and ty just to ease our calculations. Now we are declaring a variable called sum where we will store the product, aggregate it, and finally we will store it in C. The important line to understand here is what this for loop is doing. Let me make a new page. So suppose this is A, this is B, this is C, right? Each tile, let's say this is the tile. At the first iteration, it will start from the top left of A and top left of B, right? In further loops, we will slide it. In A, it will slide it in this direction. So t is equals to 1 will be this, t is equals to 2 will be this, then t is equals to 3. But in B, we will slide it vertically. T is equals to 1, t is equals to 2, t is equals to 3, right? But you need to remember is in each tile, so this is a tile. In each tile, there will be multiple rows as well as columns of both A and B. But since we have already calculated the row and column that we need to work on, we can only focus on that part. So maybe we can select this row of A and this column of B, right? We already know which row and column to work on, but we are storing all the elements in a tile. So we will store these entire elements in the tile for faster access, because in subsequent threads of a particular block will require a different element maybe. So let's say a thread only works on this row. This is the tile size, right? But the another thread can work on the last row of this particular tile. But since we have already stored these elements in the shared memory, the access will be much faster. You don't need to read these elements again from the global memory. You can just go look shared memory, fetch the elements from there, multiply them together for both A and B, and then store the sum. That way it is much faster, right? Now, so we will start from 0. So it is saying the 0th tile, then we increment the tile one by one. Now, the important part is t is less than n plus tile minus 1 by tile. So suppose uh, your matrix is, let's say, n by n, where n is 100. So 100 by 100 matrix is you have, and your tile size is defined as, let's say, 10, not 10, maybe let's keep it at 8, right? So tiles will vary from 0 all the way to 100 plus 8 minus 1 by 8. 107 by 8, how much is it? 1 3. So we'll have 13 tiles, right? So if this is the matrix, you will have 13 tiles just sliding on. So these are tiles and these are rows, and the last tile will be a little bit over the boundary of matrix A, or same goes for B. So you will require 13 tiles. Just showing that calculation as well. Now, we are just doing a quick bound check that if rho is less than n and t dot tile plus tx is less than n. A lot of people will get confused in why we are doing this check and where is this t dot tile plus tx is coming from. Suppose this is the matrix. You are in this tile. Tile equals to t. You already know which row of A to work on. So this is A. So already know A, and we need to check the bounds of row as well, as we always do. So we need to make sure that row is less than n, right? Another thing we need to check is the index of the column that we are trying to access the element from. Since we are sliding this in this direction, sliding the tile left to right, the first element can be written as t times tile size, right? And after that, since this is a block, since block and tiles are of the same direction dimension, and in a particular tile there will be multiple threads t01, t02, and so on, right? So since we are moving in this direction, we need to add thread idx dot x to get the appropriate column name, and we need to check if this column is less than n, because in the case earlier we saw if the thread id is less than n, the tile can go outside the boundary of A as well, right? And when it goes outside the boundary of A, we need to make sure we are not storing these elements or doing anything. We can just make them 0. Let's see what is happening here. So we're storing ty and tx indices in the shared memory A. We are checking if row is less than n, as well as a column, which is t times tile plus tx is less than n. Then store the row comma this particular element t dot tile plus tx there, else store 0. So in the shared memory, the index will be row comma t, sorry. In the shared memory, the index will be ty comma tx, and we need to get the elements from row comma t dot tile size plus thread id dot x. This is just that. So this thing will come from DA. There's a similar procedure for B as well. For B, we already know which column to work on, and we are sliding the tiles in this direction from top to bottom. So a particular row of this particular thread can be calculated as t dot tile size plus thread id dot y. In this direction it is y, in this direction it is x, times n. We skip over the n rows and get the element that we required by adding column. So bs ty tx will be equals to b of this particular uh, element, which is tile number times tile size plus thread id dot y, skipping over the n rows and going to the column element of b in that particular tile. So we are doing the same thing here again. We are checking the bounds. Column should be less than L, as well as t dot tile plus ty should be less than n. Then we are storing that particular element in the shared memory. Now you will observe that there is a word called sync threads. So if we don't do sync threads, then sometimes it may happen is the shared memory would not be updated by all the threads. And if a particular thread tries to reach a particular element from the shared memory, let's say this one, and it is not yet filled, then it will give us wrong output or may not work. So what we are telling by using sync threads is, please wait till all the threads have done this operations. All the threads have loaded this particular element in the shared memory right now. It should be completed. Shared memory should be filled with the required number of elements. Now we are just doing the simple matrix multiplication, just like as in the naive one that we do. We go from 0 to the tile size. We are varying the inner dimension k. We are storing the results in a variable called sum. We are doing I comma k and k comma j. We are syncing the threads again, telling all the threads to complete this operation before you move forward. Then storing the results finally in row column comma column element of DC, which is the output array as well. And then equating it to sum. So this is the easiest way I can explain this kernel as well. I know this explanation will be difficult, but you will need to take a pen and paper yourself and calculate these indexes of threads and blocks and understand which particular thread will use a particular element from the shared memory or store or load it in the shared memory as well. Rest of the code is same, just that the block size is, where have I mentioned the block size? Here it is. The block size is related to tile. So threads per block is tile times tile, where the blocks per grid required will be calculated again as n plus tile minus 1 divided by tile. And same goes for the y dimension as well. Now looking at the code. So I have this repo on pulled up on Colab already. I'm sorry, here is Diwali time here and lots of firecrackers are going on. You may hear some noise in the background. Now, this particular code is the day two part, the yesterday code that we implemented, and you will observe the speeds right now. So for larger dimensional matrices, let's say, let's wait for 8092 to complete. So 80921 is for naive, it is around 454 gigaflops per second. Now let's see how the shared memory one is doing. You will see immediate improvement, almost 1.5 times improvement. We are reaching around 716 gigaflops per second. So that is good. What do we have in the tile size? It was 16, right? Let's try to change it to 32, maybe. Yeah, significant improvement from the naive one, twice as fast as naive one. We are still around 5 times slower, but yesterday we were 10 times slower than the CuBLAS implementation as well. So this is a great achievement, I would say, for you if you are trying to implement this on your own. There is also a very great video by Simon on tile matrix multiplication. It has the visualization part as well. I tried to explain it using pen and paper, but maybe if you require some sort of visualization, you can refer to that video as well. But it will be very useful if you can just bring out your pen and paper and calculate these numbers on your own. and see which particular thread is running operation on which element of C, and how the tiles are working, and which particular thread will be updating which element in the shared memory as well. I'll update this code on GitHub and tomorrow we'll meet again. Thanks a lot.